Hi guys. Hopefully things are going okay. Obviously, if you haven't heard the announcement, we're going a little longer than what was initially anticipated. We'll have to see what happens after that. I know the governor had mentioned something in her interview about, or in her press conference rather, about making some announcement as it pertains to schools. So hopefully, didn't really give a time frame on that announcement, but hopefully we'll have some more information here soon. I have not heard anything as far as we go from the university. I'm still hopeful that we can, continue our work online. As far as I understand, that is what Lake State is doing is online classes. So that is effectively what we're doing at the moment. So hopefully that'll work for them, and we'll still be able to salvage some of this semester. I'm not sure where you guys are at. I'm not getting a lot of feedback. I know some folks had some technical issues. I still have at least a couple folks that I've not heard a thing from at all. So I would really appreciate it if you would check in with me just so I know that things are going okay and that this is useful. I know my extended family and I have been talking on Zoom, which is an app that allows people to meet like live stream. So if that would be something that would be helpful, so that you guys can ask me questions or let me know what's going on, we could set up a particular time to do that. That would be great. It's pretty wide open at the moment, so yeah, if that's something that would work for you or something that you think would be helpful, please let me know, and we can set that up. So in the meantime, we left off talking about strong acids and strong bases, mainly strong acids, right? And because we're working with dilute aqueous solutions, we need to understand something about the nature of water, and that is the autoionization of water. Auto as in automatic. So some of you may have recognized in my examples that I used in my last video that in one reaction water was serving as an acid, and in another reaction water was serving as a base, and that is because water is what we call an amphoteric compound. Okay, amphoteric, kind of like amphibian, means both. In this case, it means it acts both as an acid and a base. So depending on the conditions, water can be both an acid and a base. So what that means for water, just pure water, is that actually to a very limited extent, water is reacting both as an acid and a base with itself. So that reaction looks something like this, where one water molecule is reacting like another, giving up a proton, or that hydrogen ion becoming H3O plus, the hydronium, and the other having given up that hydrogen ion becomes the hydroxide. Okay, and so this is the reaction known as the autoionization of water. Okay. And we could write an equilibrium expression for this reaction, recognize that water is a pure substance, and so as a pure liquid it doesn't make it into the equation, and so the equilibrium expression looks like this, right? Just like we use Ka for acids, Kb for bases, for water we use the equilibrium expression Kw. And just like any other Kw, it is a constant at a particular temperature, typically 25 degrees Celsius. It also bears note that we don't often use H3O plus, right? Oftentimes we substitute in H plus. So that same equilibrium expression you will often see written like this, where H plus is used in substitution of H3O plus. Remember that for all intents and purposes, those things are the same. So Kw at 25 degrees Celsius is a constant, 1 times 10 to the minus 14. Okay? Okay, so what are the implications of that? Well, first off, let's talk about a neutral solution. Okay, so neutral solution, pH of 7, the hydrogen and hydroxide are equivalent. So yes, in your water there is hydrogen ion and there is hydroxide ion. Very, very small amounts, but those two are canceling each other out. And this is the reason why your glass of water, presuming it's 25 degrees Celsius, is neutral. Okay? And so if we substitute in Kw to that equilibrium expression, we find that the hydrogen ion concentration times the hydroxide ion concentration has to be equivalent to 1 times 10 to the minus 14. Okay? So again, for a neutral solution pH 7, that means the hydrogen and the hydroxide are equivalent, and those concentrations are 1 times 10 to the minus 7. Okay, so 1 in every 10 billion molecules of water undergoes this ionization process. Again, there's a very limited extent to which this takes place. Okay? But understand there's also a relationship. If that value, 1 times 10 to the minus 14, the Kw for water, cannot change, then if something were to happen to the solution to increase the hydrogen ion concentration, the hydroxide ion concentration has to decrease, and vice versa. So these two things, those concentrations have an inverse relationship. Okay? So the important implication of this is that because we have that equation for Kw, if we know either the hydrogen or the hydroxide ion concentration, we can find the other, the unknown. So let's use this as an example. Let's say that we had a solution where the hydroxide ion concentration is 2.99 times 10 to the minus 5 molar. Okay? And we're asked to find the hydrogen ion concentration. Now, why would we want to know the hydrogen ion concentration? Well, it's the hydrogen ion concentration that determines the pH of this solution. So when you measure, and we often do, the pH of a particular solution, what you're really measuring is the hydrogen ion concentration, which, according to Kw, is related to the hydroxide ion concentration. Okay, so we can set this up. Hydrogen times hydroxide has to be equal to Kw, 1 times 10 to the minus 14. And so we know the hydroxide ion concentration that was given to us in the problem. We make a quick substitution, and now we can use that equation to solve for the hydrogen ion concentration. In this case, we get a hydrogen ion concentration of 3.34 times 10 to the minus 10 molar. Recognize that the hydroxide ion concentration is much, much greater than the hydrogen ion concentration. And so this is going to be a basic solution. When the hydroxide is greater than the hydrogen, you have a basic solution. But now that we've found the hydrogen ion concentration, we can calculate pH, right, by taking the negative log of that value, and we get 9.48 times 10, 9.48 as our pH. Recognize that anytime you have a pH greater than 7, you have a basic solution. Let's look at one more example of this. Well, what if we had a hydroxide ion concentration that was 1.25 times 10 to the minus 12? Could we calculate the hydrogen ion concentration? Absolutely. Hydrogen times hydroxide has to be Kw, 1 times 10 to the minus 14. So we plug in our known value for the hydroxide, divide both sides by 1.25 times 10 to the minus 12, and we get a hydrogen ion concentration of 8 times 10 to the minus 3. Recognize in this situation that the hydrogen ion concentration is greater than the hydroxide, and so this is what we would call an acidic solution, right? More hydrogen than hydroxide. And of course, we could calculate the pH by taking the negative log of the hydrogen ion concentration. Negative log of 8 times 10 to the minus 3 is 2.1. Okay? Anytime you have a solution with a pH of less than 7, you have a solution that is acidic. Okay? All right, so we can use this. We've talked about how to calculate strong acid pH. Let's talk about an example using a strong base then. Okay, so here we have an example. 0.025 grams of sodium hydroxide. Recognize the hydroxide there. This is going to be a base. In 500 milliliters of water, what is the pH? Okay, so just like we did previously, the first thing we're going to do is we're going to calculate the molar concentration of the sodium hydroxide. So we must first convert that to moles by dividing by the molar mass. And we find that we have 6.25 times 10 to the minus 4 moles of NaOH. We then have to divide that by the volume in liters. Okay, so 500 milliliters is 0.5 liters. And so we end up with a concentration of 1.25 times 10 to the minus 3 molar sodium hydroxide. Okay. Now here's where the strong acid, strong base thing comes into play. Sodium hydroxide is a strong base, which means it's going to ionize completely. Because it ionizes completely, the concentration of the sodium hydroxide itself is going to be equal to the concentration of the hydroxide. So 1.25 times 10 to the minus 3 molar is also the concentration of the hydroxide ion. Okay? So now we can use this equation, H times OH is 1 times 10 to the minus 14, to determine the hydrogen ion concentration and ultimately find the pH. Okay? So we substitute in our known concentration of hydroxide, 1.25 times 10 to the minus 3, and set it equal to Kw times the hydrogen ion concentration. Divide both sides by 1.25 times 10 to the negative 3, and we get the hydrogen ion concentration. Once you know the hydrogen ion concentration, we can calculate the pH by taking the negative log. So negative log of 8 times 10 to the minus 12 is 11.1, and just like we predicted, we've got a pH greater than 7. This is a basic solution. Okay. So quick reference, if you don't remember from our previous class, that is Chem 2, strong bases that you should be familiar with: lithium hydroxide, potassium hydroxide, sodium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. Okay. So anytime you see one of those, you should have, you need to remember that those are strong bases. Okay. I'll post some additional slides that you guys can look through, or maybe, actually, I think it was already included in the slides I posted on Saturday, the strong acids and strong bases. So take a look at those as well, and it goes through a couple more examples like what we're doing right here, so that should be helpful. All right. Last thing we need to talk about, there's a relationship that exists, a second relationship that we can discuss between hydrogen and hydroxide. Okay, so here's the equilibrium expression that we had before, but we could actually take the negative log of both sides. Okay? If we take the negative log of both sides, the right side of this equation just becomes 14, right? And whenever you take the log of two quantities that are being multiplied, it's the same as adding them together. And so we can write this same expression like this. Recognize there's a negative out in front, so that negative makes the positive a negative. Sorry, that was a little confusing. Hopefully you were able to keep up with that. Okay, but we have another quantity name for negative log of hydrogen, right? That's just the pH. Well, what would be the negative log of the hydroxide? That also has a name. It's called the POH. So if you take the pH and you add it to the POH for a dilute aqueous solution, you will always get 14. Okay. So this gives us another way to calculate pH. Let's go back to our previous example. We calculated the hydroxide ion concentration at 1.25 times 10 to the minus 3 molar. Okay. We could take the negative log of that to find the pOH. Okay. So negative log of 1.25 times 10 to the minus 3 is the pOH. In this case, that's 2.9. If we subtract that from 14, we get the pH, which is what we just calculated at 11.1. So recognize that this is a second way to calculate pH using the hydroxide ion concentration. Also recognize, sorry guys. that the pOH has a scale as well. Okay, pOH scale is also going to go from 1 to 14, 7 being in the middle. 7 is still going to be neutral, but now the scale for the pOH is flipped. 1 to 7 is going to be basic. So recognize that a pOH of 2.9 fits it between 1 and 7. That makes it base on the pOH scale. On the other side, 7 to 14 is going to be acidic. Okay. This will probably be the first, last, and only time that I talk about a pOH scale. It does exist. I imagine that there are certain applications for it, although most of the time we use the pH scale, right, which is the exact opposite. And so we'll focus primarily on calculating pH. But I do want you to recognize that there are a couple of different ways that we can get to the pH. Okay? That should be enough information for you to finish up the sheet that I posted on Saturday. Okay. We'll see. I don't know if I'll get to it tomorrow or Wednesday, but our next discussion will be on looking at weak acids and weak bases. So far we've only talked about strong acids and strong bases, which are relatively simple because we can relate the concentrations of those hydrogen and hydroxide ions to the concentrations of the strong acids or the strong bases. It's not so simple when we look at weak acids and weak bases. So we'll take a look at that in our next lesson. Again, guys, please get in touch with me. Let me know that these videos are working. Let me know if there's a time when we can do some live conferencing so that I can answer questions either about the material or what we're doing moving forward. I don't know that I can answer all your questions. I don't even have all my questions answered yet, but I will do my best, and I'd like to hear from you guys. So, all right, hang in there. We'll talk again soon. Bye.